All right, section 7.8, molar mass and density in gas law calculations. This is a little bit of a tricky sort of problem. It still centers around PV equals nRT, but it includes some manipulation. So we'll go ahead and do a couple of examples of this. But after this, you'll be able to use the number of moles in a chemical reaction along with a balanced chemical reaction to determine the number of moles and the mass of any other reactant or product in that reaction. Okay, mass in the ideal gas law. If the identity of the gas is unknown, you can use molar mass to convert mass to moles, then determine pressure, volume, or temperature of that sample. If the identity of the gas is unknown, use the ideal gas law, the PV and T of the sample, and the mass to determine the molar mass. Okay, the density of a gas, which is given in grams per liter at a specific temperature and pressure, provides the mass, pressure, volume, and temperature of a gas sample. And if the volume and mass or moles of a sample are known, density can be calculated. Okay, so this is basically, you can do a lot with PV equals nRT. Now, to get down to brass tacks with this, okay, so we have, I'm going to start out with PV equals nRT. Now, R is equal to 0.08206 liters atmospheres mole Kelvin. Calculate the volume. Okay, so what we're looking for is V equals question mark. That 48.3 grams of sulfur dioxide, what is that? Ooh, that will be SO2 gas occupies at a temperature T equals 0 degrees Celsius, which I'm going to convert that to 273.15 Kelvin because I want my temperature in Kelvin, and at 1 atmosphere pressure. Okay, 1 atmosphere, P equals 1 ATM. Now, essentially, what we need to do is rearrange the ideal gas equation so that V is equal to nRT divided by P. Okay? Temperature is accounted for, pressure is accounted for, R is accounted for, but N is not accounted for. Now, I'm going to show you a way to do N fairly easily. Well, N is equal to number of moles. Now, we can solve for number of moles by taking the mass and simply dividing it by molar mass. Now, we have our mass, which is 48.3 grams. Do we have our molar mass? Well, we don't have our molar mass, but we have the identity of our gas. And by having the identity of our gas, which is sulfur dioxide, we can deduce that our molar mass for sulfur dioxide is approximately 64 grams. So effectively, this right here is equal to N, so it gets plugged in right there. So we can rewrite this as volume is equal to 48.3 divided by 64. I'm going to put that in parentheses, times R, which is 0.08206. T is 273.15, and I'm going to divide all of that by my pressure, which is 1 atmosphere. So 48.3 divided by 64 times 0.08206 times 273.15 equals 16.9. What are my units? I'm going to call that 16.92 liters. All right, so you can see that there's a little bit of trickiness to this, and there's a little bit more to the problem than is being presented. You know, there's a next step that you have to get into. Next slide. This question right here a 93 gram sample of a pure gaseous substance. Okay, so that tells us a little bit about the gas, but it doesn't tell us specifically what it is. Occupies, V was 29.5 liters. Now let's go ahead and actually rewrite our gas law equation. PV equals nRT. Okay, so we've got volume. Temperature is 27 plus 273.15. That would be 300.15. Pressure is 1.25 atmospheres. What's the molar mass of the gas? Okay, so let's go ahead and let's work through how we need to manipulate this equation. PV equals nRT, so we need to isolate the N. But we actually have a part of that N because we have the mass, but we don't have the molar mass. So I'm going to rewrite my equation. PV over RT is equal to N. Okay. Now I'm going to plug in values. So I have my pressure, which is 1.25, volume, which is 29.5, my R value, which is 0.08206, my temperature, which is 300.15, and my N value, my number of moles, is going to be my mass of my gas, 93, divided by molar mass. So molar mass is the part that I don't know. And so that's what I'm going to be working to solve for. But the first thing that I want to do is I want to kind of clean this up a little bit. I'm going to say 1.25 times 29.5 divided by 0.08206 times 300.15. Okay, so that gets me 1.497139. Okay, that is equal to my N value, my number of moles. So this, I have the number of moles, but I don't have the molar mass, which is what I'm looking for. So I can say 93 divided by my M molar mass. So now I divide molar mass. I'm going to write it shorthand as MM. I multiply that by both sides. And then I divide by 1.497139. So my molar mass is equal to 93 divided by 1.497139. 1.497139. And that gives me my molar mass, which is 62.12 grams per mole. Next up, it's a little bit different. Here we've got density. Okay, let's look at our units for density. Our units for density are grams per liter. So that's a mass per volume. Okay, now PV equals nRT. Calculate the pressure at which oxygen, do we know what oxygen is? Yes, we do. It's O2, which has a molar mass of approximately 32 grams per mole. Okay. We have a density, we have a temperature, which is 295.15 Kelvin, because I did 22 plus 273.15. Now, what I need to do is solve for P. P is equal to nRT divided by my volume. Okay, now let's see. I have effectively a volume because I have my density. So what I want to do is I want to use this information that I have and I want to basically plug it into PV equals nRT, or P equals nRT divided by V. Okay, now this might seem a little bit strange, but this N value we actually kind of have. We have that because what we can do is we can convert from grams to liter, from grams per liter to moles per liter. The way that we do that is by using our density. Our density is, or the density that we're being asked about is 1.44 grams in 1 liter. Because this part of our equation, N over V, is moles per liter, which is what we're aiming for. We also have our molar mass of O2, of oxygen, which is the gaseous, or the gas that we're working with. 32 grams of O2 is 1 mole of O2. So when I solve this, when I take 1.44 and divide it by 32, I end up with, well, 0.0450 moles in 1 liter. So now effectively that I've gotten over that hurdle, this becomes much simpler. P is equal to 0.0450 moles. My R value is 0.08206 liters, atmospheres, ATM, moles Kelvin. Multiply that by my temperature, which is 295.15. What's my volume? Well, my volume is simply 1 liter. So 0.0450 times 0.08206 times 295.15 divided by 1, and I get 1.09 atmospheres. Now this is, I would argue, one of the more challenging sorts of problems because of the fact that what you're doing is you're taking a density that you're provided with and you're having to convert that from the density units that that we've been working with over the course of the semester, grams per liter, and you have to convert it to moles per liter. And that just seems, there's kind of a barrier to that. It seems almost as if you're not given enough information to solve this problem, but you are. And that's because one of the things that you have to do is you have to recognize you have the identity of the gas, therefore you have the molar mass of that gas. You're given a density, which tells you a volume, 1 liter, and the mass of that gas that occupies that 1 liter. All right, I hope this is helpful, and I'll see you in the next section. You got it.